move my screen a little bit here. There we go. Nice. How's everybody doing? So for those who don't know, it's been a little while, but a while back, I was doing some streams on this book, which is a very good book. And you can find those over on YouTube. I should probably put the link in here. So let me go drop that in. I've got a bunch of these streams where we kind of were going through chapter by chapter, this book here. And one of the, I think we got up to chapter 8 last time. And then it's been a couple of weeks since I've done one of these streams. So just due to a combination of good things, but some travel and just some busyness and a lot of awesome stuff happening at planet scale, haven't been able to do them the past couple of weeks. But I did want to finish the book. I still want to finish this book. I don't always do it, but I like to finish what I start, at least if it is a good, worthwhile book to read. And it does seem that way. It's really good. In fact, you can tell a book is good when it starts to do this. The cover won't sit flat anymore because I'm constantly flipping it out like this and reading it. So anyway, welcome back to the stream. I hope you all have been good. So I'll just hang for a minute or two, let people file in. But the goal for today is to partly talk about chapter 9, which is all about consistency and distributed transactions in a distributed databases environment, which is pretty fun. And then there's, I think, 3 more chapters after that. So hopefully we can knock this out before the end of the year. And then in the new year, pick a new book. So we could also talk a little bit about that. I do want to find sort of the next book to do a stream on. And one of the things I was thinking about is trying to figure out what to do a book on. I don't think I want to do another just like pure databases book, right? This is like a really, really good databases book. It kind of covers a little bit of everything. It covers single node databases and distributed systems and data structures for indexes. Like, this is a really good overview book, and it gets into some like nice technical details as well. But I've been trying to think about what other books to do. One thought that I had, let me, how do I switch over to, oh, I need to share my screen. Man, I need to do this more often. Share my entire screen. I'll share that one. Okay, and then let's go over here. And then add the stage. One of the ones I had thought about is this book here, Build a Large Language Model from Scratch. It seems kind of fun, in part because, like, you know, I enjoy using AI. A lot of us work with AI regularly these days. And it's like, I understand the basics of it, but I don't feel like I understand it super deeply. And what better way to learn it than to build one? So I'm not convinced that this is going to be it, but I had this idea a couple weeks ago. Oops, zoom in here a little bit so y'all can see better. But it doesn't have to be AI based, right? It could just be a different kind of systems book. Oh, there's also a book that recently came out just called Latency, which I thought would be pretty cool. It's all about like latency in cloud environments and distributed systems by Pekka Engberg. I thought that could be a cool one to read. But anyway, you should give me your suggestions and ideas if you have them for what we should do next for this. Let's see, there's some questions here. Can you make a video on how to become a good backend developer with Java and how to become better instead of stuck in tutorial hell? That would be an interesting video to make. Yeah, a part of it is just, you got to go and build stuff. And, you know, tutorials and all that kind of stuff are wonderful. It's awesome. I like tutorials. But I think there certainly is benefit in just starting to build, even if you don't feel super confident in it yet. One option is contributing to open source software. And another option is just go build something, even if it never sees the light of day as like a real product. If you're into databases, like go implement a B tree, like a real B tree that can do fast lookups, and you benchmark it and you test it, right? If you're into distributed systems, go like build a distributed key value store. Writing a compiler in Go, I hear, is good. That would be fun. I will have to admit, writing a compiler in Go. Is that a book? Because the other thing is I don't actually really know Go. So that would be cool. Oh, this is Thorsten Ball. This would be good. This would be good. Let's do this here. Let's add this to the stage. Should we do it? Should we write a compiler and go together? It'd be kind of fun to learn Rust too. Is there a how to write a compiler in Rust? It'd be cool. But yeah, so I don't know particularly what we're going to do next, but something like this. Something that's still systems-y, right? Like, but not just another book that's on databases, because we just spent so much time like going over all these database topics here. Anyway, let's go over here. Oh, new Gemini dropped today. We are back. Yes, we are indeed. We are back. So maybe we should start talking about chapter 9 though. So let's see. I'm going to go over to, I've got the book pulled up here. So chapter 9 was a good chapter. It is can get a little bit dense at this point. I think it's actually going to get more interesting at the end of the book, because chapter 8 and 9 were very sort of theoretically oriented. Like they gave some practical examples, but a lot of it's about thinking about, in theory, how do we handle failures and what are the like algorithms that we use to do consensus and distributed transactions, two-phase commit, all of these kind of things, which are cool, but it's not really talking about like the database systems as a whole. So I'm excited to get into, if we look at chapter 10 is about doing batch processing, so a little bit more applied. Chapter 11 is doing stream processing. And then chapter 12 is sort of future looking, which actually would be kind of cool to see, because this book was written in 2017. It's like maybe some of the future looking stuff is actually here today, here now. So what I want to do though, one of the big things that's like important to understand for this chapter, and it's like a good sort of concept to just know the theory of if you're doing databases, is the idea of linearizability. And this is something that, again, this book has a lot of sort of theoretical concepts. So this is a theoretical concept that is something that we want to achieve in databases. So they kind of go over in the book, Martin goes over in the book what linearizability is and kind of explains how that's different from serializability. And then from there, jumps into talking about why is this so hard to achieve in a distributed system. Let me zoom out one more so we can get this better here. Oh, it's not letting me move this. Okay, so let's bring this over to, let's bring this over to Excalidraw. Let's just do that so that we can draw on it. It'd be more fun. As we're going, drop questions. I honestly don't even mind if we like end up taking one of these streams and talking about something totally different than what the main subject was. I just like talking about databases, in case you couldn't tell. I was also at KubeCon last week. That was fun. I don't know if anybody here was at KubeCon, but got to have lots of good conversations about databases and Vitess and Neki, which is our sharded Postgres. A lot of cool things happening. But okay, let's hide that. Linearizability, a big part of what this is essentially, it can be a little bit confusing to distinguish this from something just like serializability. So I'll try to make sure to describe this well. But it's essentially ensuring that if you have like a given object, a given piece of data, a given database, that all of the actions that took place on that, the reads and the writes, can be sort of described in one linear sequence cleanly, right? Where like, it's not like, oh, we're getting conflicting reads and writes and all of this stuff as we go. Because once you start operating data that's distributed across many nodes, that starts to become a lot harder to achieve than if you just have a database sitting on, you know, the simple case of like, you have one server, has all your data, that one server is in charge of all the reads and all the writes. It's fairly easy, right, in theory, but to ensure that all of the reads and writes are happening in some totally ordered sequence, right? So the example that it's giving here is an example of something that's not linearizable. So what they're talking about is like, okay, let's say we have some like database system. Maybe this is, you know, the database powering ESPN.com. And to people, Alice and Bob are watching, I think it's the World Cup. Yeah, they're watching the World Cup and they're tracking the score, right? They're hitting refresh and they're getting their scores updated on their phone. So there's a game going on. Oh, wow. Why is that so large? There's a game going on and the game just ended. And so the final score has been like sent to ESPN's database to register like this game is over and here's the final score. So that gets uploaded and we're going to assume that there's some kind of distributed database powering ESPN. I don't know what ESPN's database is. Maybe they should use PlanetScale. I should talk to them. But anyway, so this goes to whatever your leader is, right? Let's just assume it's like you have a single leader and then you have some replicas, some followers. And so we get a commit back. But in this case, this is assuming we're using some kind of, like this is asynchronous replication, because you can set up a database where it would not give a acknowledgement back to whoever's, inserting this final game score until all of the other replicas are in sync with it. We've talked about this on other streams before. That has a lot of performance downsides because any delays in the network and all this can slow down your ability, your write throughput pretty significantly. So anyway, we've confirmed. So in terms of the referee or whoever is responsible for making sure this game has finished, they think, okay, great, we're done. But then there's some replication lag a little bit to the first follower, but maybe this replica is either in a really far away data center or there's just some kind of network congestion issues, something like that, making it where it took a long time to get over there. So the problem is you then have, it's using Alice and Bob as the example, but you have some customers, right? They're sitting on ESPN.com, they're hitting refresh, trying to figure out what the final score of the game is. A lot of times in these kind of applications at real high scale, a lot of the read requests are getting served by replicas because that offloads work from the leader. And so if Alice hits refresh and her request hits follower 1, she's going to see that the game is over, Germany won the World Cup. But then Bob, who could be sitting right next to Alice, right? They could be in the same exact place looking at their phones together. His request from his phone hits follower 2 and he has no update on what the game is, right? And then if he, did another request later on after follower 2 gets updated, then he would see it, right? And this doesn't really have a time scale on it. Like generally, those kind of things wouldn't be huge amounts of lags, like milliseconds or even seconds. But there are cases where, like, if this follower like somehow got partitioned from the network and actually just couldn't communicate with the leader for 5 or 10 minutes, what if you end up with some people who 5 minutes later still in their app don't see that the game is finished, right? So this is one of, there's a lot of problems in distributed systems, but this is one of the big problems that is difficult to solve while also maintaining good performance in a distributed system. Because you could go to it's easy to just go to an extreme case of, and we're going to talk about some algorithms in here about committing across multiple nodes, but you can take this to a big extreme of just saying, okay, the leader will receive writes, and then we're never going to acknowledge that back until we know that all of the replicas have that information. But there's still some issue with that. Let me erase all this stuff here. Oh no, I erased the picture. Didn't want to do that. Let's just undo all this. So one thing that you could do here is you could say something like, okay, let's change this here. So this okay, change this to red. This okay is not going to happen there. We are going to have our leader wait until it receives a reply back from all the replicas saying, yeah, I've gotten the information that the game is over and this is what the final score is. And now I'm going to come back here and the referee or whoever it is on the sideline, punching all this information in, won't get the confirmation that I have received your data until all of the replicas and followers have received it. So that is a possibility, but there's actually still this issue. That doesn't actually solve this replication issue, because unless there's some kind of coordination where it's like, okay, follower 1, you received the information, but don't let any requests see this new row until then later on after the leader has gotten all the acknowledgements back. then it could send a message out saying like, okay, now you all can reveal that you have that row. In other words, that's the commit point. And that's what we'll talk about in a minute. With two-phase commit is one way of doing this in a distributed environment where you send writes to all of the nodes, but then you need a way to say, okay, when can I actually publish to people who are sending me requests that I have that information? So then there's a whole nother step of like communication back and forth saying, okay, now we can tell the world, right, that we have this information. So you can go to these extreme cases where you have all of this, like these network requests back and forth to wait until you've gotten acknowledgements from all of your other nodes that have the data, and then do more communication to ensure that things are committed. But as you can imagine, that makes things look a lot slower, right? Instead of the write taking, a couple of milliseconds like it did over here, it might go from looking like it's a, including network hops and all that kind of stuff. It might look like a 5 or 10 millisecond operation here to all of a sudden going to a 500 millisecond operation, because there's all of this other overhead and communication and all of this stuff, right? So anyway, there's like, that's kind of the whole premise of this chapter is we have this thing called linearizability, which in an ideal world would be very nice if just all databases could be linearizable. Every time any client, Alice, Bob sends a request to the server, they always see the same thing. It's always consistent. There's always a nice, neat ordering of events. But because of physics, basically, that's actually not that easy, right? It's kind of hard to do that. Okay, interesting. We have a very specific Postgres question here. Let's see if this can be answered quickly. Oh, wow, it's big, like blocks my whole head. YouTube videos for performance tuning, nice. Let's see. Postgres, when you set auto commit to 0, you need to commit every query. And this is happening in Postgres. Partitioning strategies too. Yeah, so that like if you don't want things to automatically commit, then you have to do explicit commits. And that's something that probably most people don't want, right? Like I think, well, I guess it depends on how much you know about databases. A lot of people probably expect that if I'm running a single, select query or an insert query, and it's not surrounded explicitly by a begin transaction and a commit, that should be treated as its own isolated transaction. So I would recommend just using that. And then if you need a transaction that has multiple statements, using explicit commits. Maybe I should clarify for people who don't know what I'm talking about here. What are we talking about? So this is just a little tangent, but it's fun because there's probably some people in this call or this stream who know lots about databases and maybe some that don't know that many. So let's see. Yeah, we'll just do a select. Why am I on orange? Let's be on blue. Okay, so here we have a database query, right? Select star from users where ID equals 10. This is a very simple query. You can have more complicated queries, but by like if you have auto commit on, this is like a database feature. This is going to be treated as its own isolated transaction. We've talked a lot about transactions in other videos. We won't go over all these details, but sometimes you want multiple different statements to be treated as a single isolated atomic operation on your database. So what you might do for something like that is you would say, how do I do this? I forget if it's begin or start, actually. I think it's begin transaction. Correct me if I'm wrong here. I'm actually writing an article, which is odd that I can't remember this. I'm writing an article, another interactive article about transaction isolation and how that's handled in Postgres and MySQL. That's a lot of fun. I'm using lots of cursor for it, which is Composer 1, by the way, is awesome. Anyway, let's add some stuff down here and let's say commit. So what you might do is you might have something where you like, I'll move this, change this font color just so we know something different. You begin a transaction, you select some information about a user, and then maybe based on that information, you decide like, oh, I'm going to insert into my user log a user ID and a note. And then your values are like your user ID of 10. And then you have some note for the user, right? Anyway, you can have a bunch of these transactions all, or statements, I should say, all in a single transaction. So the way that this works is this is a simple case where we have a begin, and then we have one statement here, and another statement, right here. And we could have 10 statements or 100 statements in this, but all of these will be committed together when we run commit. Or if we say rollback, we can decide dynamically at some point, oh, we actually don't want to do any of this. Rollback will cause any modifications that got made during this transaction to get undone. So this is a generally supported feature in relational databases, right? This goes for MySQL, this goes for Postgres, right? And when you have auto commit on, my understanding about how both of those databases work is you're making it so that if you run an individual statement like this without an explicit begin and rollback, that's just going to treat this whole thing as a transaction. It's as if you put begin transaction up here and then you put rollback down here. So let's look at this. Yeah. So anyway, good question. Hopefully that answers your question. I kind of want to just do, I think like what's actually almost more fun than doing like a structured going over a book is just like a database AMA. Not that I'm like the world's database expert. There's plenty of people that know databases more than me. You know, it would be really fun. Should just bring like a guest planet scale engineer on every time. And then you all can just pick their brains about what they do. That'd be cool. Yeah, I was just chatting with someone who joined Planet Scale recently earlier. He's worked at a couple of other companies, run some very big databases. It's always fun just to learn about both at Planet Scale and outside of Planet Scale, like seeing databases being operated at scale. It's really cool. Kenway has a great question. What happens if this transaction is a cross shard and each shard has sync replicas? Amazing question. Perfect. I was even thinking earlier we should talk about, not heavily, but this is a good question because this is what I just described, this whole begin transaction, rollback, treating all of these operations as an atomic unit of action is, again, easy in quotes, like all databases are kind of hard, even on a single node, but easier to do when you're just on one node. When you're in a distributed environment, and if the selecting and the inserting, like right near here, we're just selecting one row and we're inserting one row, but you can have transactions that select multiple rows and insert multiple rows into different tables and all of this. When you're in a sharded database, let's zoom out. How do I find my other pictures? Where's our sharded? Yeah, so let's go like here. So when you're in a sharded database, this becomes trickier because you might have, get our drawing thing out, you might have one of these queries come in. I need to make that a little thicker. Let's make this, make it green. So it comes in, and then let's say you need to insert data on like this shard here, but also some of the data you're inserting goes to this shard. So you want this to be something that can commit in isolation. And each of these individual nodes, if you're using something like Vitesse, each of these individual things are just MySQL instances. So they have their own ability to begin a transaction and not commit that data until we get a commit. But what if you come in here and you say like, okay, go ahead and we start a transaction there and we start a transaction there. I'll go blue. We then write some data to that one and we write the data to that one. But then we decide we need to roll back. Well, what happens if I give the command to roll back to both of these, but like this one responds and says, yep, I rolled back. And then what happens if this one never responds? Or maybe it does respond, it's just slow. There's network issues. It takes, instead of, maybe this one takes 2 milliseconds to respond, this one takes 2 seconds to respond. Well, now this proxy is sitting here holding on to the query for 2 seconds, which is an eternity in the world of MySQL and Postgres databases. And that's going to really hurt performance, right? And this is actually one of the things there was a period of time, if we're talking about Vitess specifically, we've talked about it again on stream before, a very popular way of doing basically this, right? So having a sharded database for MySQL, lots of companies use this for big sharded databases. GitHub uses it, Slack uses it, HubSpot uses it, Etsy uses it. Many, many other big companies use Vitess to shard databases. And there was a period of time, I think a long time ago, supported distributed transactions. And then for a while, it was just performed so poorly that they took that feature out. And they've started to reintroduce a sort of better version of it. I think maybe a year ago or so, it was reintroduced. But it's still something that, like, even if you have a good algorithm for doing it, it's generally recommended to, if you can, avoid distributed transactions. Because even when everything is working properly, it just adds overhead and more network congestion. So it's much better to try and keep it where your queries are all isolated to, if I am going to do a transaction that has inserts and updates and deletes, it's much better to have that basically be isolated to all of the inserts and updates that I'm going to do in one transaction, stick to a single database. So that way, if that one is working fine, it all works fine. If that one has problems, oh, well, that's out of my control, but I'm not spreading my potential problem surface area in synchronization across multiple nodes. So it's a very good question. We need more people in the chat like Kenway asking questions. Let's go back to, where are we going here? This is where I want to be. Yeah, okay. So we had a little divergent conversation into transactions, which is fun. We talked about linearizability. What we should do is let's revisit this issue where we were over here and we talked all about the complexities of this. And one of the things I mentioned, which the book has a nice-ish solution for it, is what happens when you get to this point of, I have a leader, I have followers, I know that the data has been replicated to all of them, but we need to hold off on letting the world know that we all have this data until we're in sync about it. Like the leader has to be able to know, leader right here, the leader has to know, okay, all of my followers have the data now, but we're not exposing that publicly yet because we want to be in sync where either we all give the answer, yes, I have the final scores and this is what they are, or we all give the answer of, no, I don't have the final scores yet. So we have to synchronize the point at which we're going to transition from showing this new row to the world to hiding this new row because it's not yet committed, right? It's a good tangent that we went off onto, because this is basically, how do we do this? How do we make these nice guarantees of beginning transactions and either rolling them back or really committing is what I want to talk about right here. So I'll switch this back to commit. How do we do this in such a way where it's consistent across nodes where networks can fail or can be slow and all that? That's the much harder part, right? So that's what we'll talk about here in a second. I'm just going to check a message. Okay, cool. Lots of chats going around. So the thing that I want to talk about next, and if you have your book, let me just get the page up here. Let's go full screen for a moment. If you have your book, this is where is it? What I'm looking to talk about is two-phase commit. So 356 has a nice graph of this. Let's look at two-phase commit. Funny thing is about doing a reading group on a book like this is there's a lot of people that, post pictures of this book or other books on the internet. And I'm kind of curious, how many of those people actually finish the book? Because this book is it's pretty dense. It's 500 pages. It has a lot of very good stuff, but it's also there's some parts of it that are a little bit dry. I would love if we could somehow have data on how many people actually finish this book. Ooh, this is a good question. So before we get to the other part, can we make a follower one in sync and other followers async? Yeah. So that is called semi-synchronous replication. So that's a popular way of doing things. And that's actually a very good balance of, performance, but also data durability. So you can have like a primary and two replicas and make it where I just need one node to acknowledge, right? Or if you have 5 replicas, you can give it a number n. You can say once at least 3 people have acknowledged, or 3 replicas have acknowledged that you have this, then I can reply back. And what that helps you be is you can know that you have better data durability than just one copy of your data, which you always want in a distributed system. But it makes it more tolerant to, like, if all of a sudden one node, there's a network partition and we can't reach one node or the server crashes, that's not going to stop the whole system. We can still keep making forward progress. So that's actually like probably on average, the best thing to do in a distributed system is make it some sort of semi-synchronous replication. So yes, the answer is yes, it's a good hybrid approach, and there is a name for it, semi-sync. So going over to, oh, I guess you can't see screen right now. Uh-oh, video looks like it's getting a little laggy. I think I fixed my audio delay issues, or at least it was. Now things look like they're just getting very slow. Okay. Man, maybe I just need to get a better streaming computer. I'm just doing this all off of a like MacBook Pro, which is like a pretty good, but could be better. Okay. So let's look over here. I'm going to zoom in. We're going to take a screenshot and we'll bring it over to Excalidraw. I just need to buy like a, I don't know. Need to buy like an M5 Mac Studio that can just crush anything that I throw at it. So hold on, get this in here. Okay. Bring this diagram in. Oops. Okay. Get this almost there. Okay. Go back to this. We have some comments. Let's see. Just finished reading chapter 1 yesterday. Was intending to watch your explanation, but I found you live. Oh, nice. Awesome. Yes. So go back. I'll put it back up on the screen. You might already know, but you're coming from YouTube. So I assume you already know what my channel is. But yeah, that's the channel. We've got streams. I apologize. The quality and audio, there was audio sync issues on some of the streams. I've only been doing live streams for like a few months. So I'm not really an expert. You know, some of these people that live stream all the time have like a team of people that work for them doing their live streams. So anyway, it's just me. Maybe I'll have a team someday. I should hire a team. But yes, so I'm glad you found it. But yeah, go back and watch the chapter 1 as well. Good work, man. I got to go study. You teach concepts that universities don't even teach us a little. Funny thing is, LinkedIn user, I used to teach at a university as well, but I wasn't teaching distributed systems. So I understand what you're saying. Maybe someday I'll go and retire and teach again, but just be like an epic university teacher. It is very fun. Teaching at a university has a lot of things that are very fun about it and rewarding. Okay, so let's look at why is the framing of this seem wrong? Something seems wrong here. Okay. So what we're going to talk about, right, is up here. This is basically an algorithm for solving this last little problem that we were talking about. How do we all in sync make sure that all of our nodes publish to the world and say, hey, I have this data available now. And so what this is called is two-phase commit. And there's variations of this. There's an algorithm called three-phase commit, which is like an even more secure or like safe version of two-phase commit. But as you might imagine, it performs even worse because it's got more phases. But and even I like had heard this term a lot, and I've never implemented two-phase commit. So like it's not like it's all that complicated, but I didn't actually like know really what it was. But basically, it's a way of synchronizing when you're going to commit across multiple transactions. So we have a simpler case here of just two databases or like two servers that need to have data in sync, right? Over here, it was like a leader and followers. So this is like a slightly simplified example, but it's kind of similar because it talks about you essentially need a coordinator software running. And in this case, it would probably be where our coordinator would just be our leader, right? But it's sort of a separate little instance of software that's managing the coordination of two-phase commits. So this phase here, like the coordinator sent some data to database 1 to write, it sent that same data to database 2 to write. So this is our primary sending that data to replicas. And in this case, it both performed well, but this section here, we would have to, like over here where we had follower 2, like the network was really slow. If that was really slow, we would have to wait for that, right? Because we can't commit anything until that data has come back. So we need to wait up to here. And then after, the whole two-phase commit thing, and we'll see why this is important, is because the commit happens in two phases. You might think, well, wouldn't it be nice if once I've heard back from all of the followers, can't I just send a message to all of them and say, go ahead and commit? But because networks are unreliable, because networks to our different followers have different performance, because messages can just get dropped arbitrarily, we could do that, but it wouldn't necessarily be reliable. We'd be much more likely, or we still have a decent chance of getting into these kind of similar situations. So essentially what we do is we break this up into two phases. We say, okay, I'm going to send a prepare message and make sure, are you all prepared? My lines are too thick. They reply yes. And then they're able to say commit and then go back here, right? So you can see this too. It also kind of, one of the reasons why this can be poor performing is because during this whole time, any data that is written in database 1 or database 2 has to hold a lock on the data, which means no other transactions can make modifications to this from here all the way over until we actually send the commit message, right? Which again, especially when like networks are slow and nodes are far away, ideally this is like only a couple of milliseconds, but this is one of the problems of databases that rely heavily on like distributed transactions, is this can turn into tens of milliseconds or hundreds of milliseconds to get these things committed, which not only means the query goes slower, but it could also back up and slow down other queries if in the meantime there's like other queries that are coming into this database and they're depending on wanting to write to that same row, they get held up for this entire time, right? So this is essentially an algorithm for, it doesn't actually totally eliminate the possibility of data inconsistency, as far as I'm aware, because there's technically still issues, and the book talks about this. Like, let me clean up this timeline here. Things could be going well, right? We write data, we send all these prepare messages and reply, but what happens if like right here, one of these, like this server crashes right here, right? We've sent the commit message out. So I guess depending on how it's implemented, right, the coordinator will assume, hey, it's been implemented, but then this database, when it starts back up, might have to like replay logs or something. Or also, what if it crashes over here, right? If this server crashes right here and doesn't send a yes reply back, this database will end up holding on to a lock on the data much longer than it needs to, which could hold up other transactions. And I'm actually not totally sure, like there's probably different ways of handling this, right? There's probably some algorithms where you could say, as long as I've gotten a majority back, I'll go ahead and proceed with the commit, which since these two are still the majority, they could go ahead and commit and move on. If they need all participants to be a part of the commit, which is what you actually want if you want like true commit semantics, then it just has to sit there and wait for like that node to recover, or for an administrator to do something, or for this database node to get kicked out of the cluster so it's no longer a part of this group. And then another server has to be spun up and caught up with the data before it can proceed, right? Like there still are edge cases where things can go awry with this, but it's at least a method of ensuring or having like a much higher likelihood of like safe commits. But as you can see, there's a lot of like network messages back and forth. So like just to commit a single write, like one row insert, like we had over here, and then to do this commit, this is all just within the database, not even like all the networking that it took to get from your app servers through a network load balancer and proxies and whatnot to your database, just within your database. This is like 6 network round trips that have to happen like within your data center. So it adds overhead, it makes things slower, but it's like everything in database and tech is basically, it's a trade-off, right? So let's see. There's a question on transactions with stored procedures. That's honestly not something I'm super familiar with. So I don't have a really good answer for you, but maybe you should do some research and write about it. That's actually another cool thing. Let me pull this up. Where is it? This is like very much a tangent, but it's a good thing for if you're like watching this stream, it probably means A, you're interested in databases or distributed systems in some way, shape, or form. And B, if you're watching this stream, it probably means you have some interest maybe in writing about the things that you do, of explaining, of teaching, and these kind of things. So I tweeted this the other day. I'm always like on the wrong monitor. Why does that keep happening? How to write great technical articles. Surround yourself with people smarter than you. Ask yourself, what would they read, and write about it. That's kind of what I do at PlanetScale, or just in general, right? There's lots of people, whether it's at PlanetScale or other places, that are either smarter than me in general, or at least in certain aspects, like certain areas of databases or certain areas of distributed systems or certain aspects of running Kubernetes clusters, are much more knowledgeable than me. And so if you just think about like what kinds of things would those people be interested in reading, and hopefully it also aligns with something you're actually interested in doing. And if those two things align, go and do it. So I don't know, Kenway, you could do some benchmarking or try things out or do some research. Let's see. Another big question here. Trying to avoid ACID transactions since they can cause locking and performance problems. Okay. Yeah, so there's different like transaction isolation levels, and we've talked about this on some streams. You're probably already familiar, Robert. And yeah, so the more strict you are with your isolation level, that generally leads to more locking and performance issues. Okay. So a ledger pattern could use optimistic concurrency, with each thread doing a single strongly consistent conditional write to make sure it has exclusive access to the next ledger sequence number. Do you see this pattern often? So there are lots of different databases that do lots of different, get this up here. There's lots of different databases that do lots of different things with how they do writes. What you're describing there isn't exactly the same thing, but I'll use a similar comparison, which is a lot of relational databases use like MySQL. It stores all table data if you're using InnoDB. It stores all table data in a B tree, which is great for some things, but not necessarily great if you have a lot of contention among rows. And a lot of it depends on your write traffic patterns and all this. There's another data structure that's used in databases like ClickHouse and other databases that are sort of aimed more at analytical kind of workloads, called LSM trees, log structured merge trees, which are designed a lot more for sequential data and sort of log type data, where it can ingest a large amount of data, and it has a tiering system where it keeps sort of the first tier of data in memory and then is also like flushing that to disk for commit purposes. And then as that, and it's in a tree that grows, and then those get merged into larger and larger trees. So I guess the point is lots of different databases use different data structures, and it depends on the write traffic pattern and the read traffic pattern. So for like what typical workloads are, at least historically, on databases like MySQL and Postgres, even SQLite, although that's more for like local stuff, are short transactions that do small number of row inserts, read small sets of data, or maybe do aggregations on big sets of data, but only return small sets of data. And it's designed for sort of powering real-time or near real-time updates, right? Like the thing that powers the app when you load it up, right? The thing that powers the UI for StreamYard, which I'm using for this stream, right? But then there are other databases that have different purposes. So like, it's all just trade-offs, and you probably know this. So if you have a very particular problem, or like very well, what's my traffic pattern? Well, I have a lot of time series reads. Like again, maybe you're reading in a lot of sort of log type time series metrics data. Well, then you probably want to choose a database that has a data structure under the hood that's designed for that. I'll just use ClickHouse again as the example because it's a great database for that kind of stuff, right? But then if your data needs are a lot more, hey, I need very structured data that's modeled in kind of a relational way, and it's not all just time series stuff. I have queries that are coming in with new writes, but I'm also updating old rows, and the traffic patterns kind of vary. Then maybe like a MySQL type database is better, right? And then there's databases that are built specifically for data analytics, which you can like export from MySQL or Postgres. So I'm sorry, that was a big long rant. But like what pattern and what data structure you're going to use all depends on what's your workload. And then you work backwards from that and you pick a database that is going to fit that workload well. And then one thing I'll say about Postgres, and there's pros and cons to this, Postgres has a big extensions ecosystem where there's people that are working on extensions, for example, to Postgres, but that also work well for analytics, where they sort of rewrite the data for analytics purposes. There's lots. I think like PG Mooncake is an example of one where it's more of a like time series analytics engine where you can still use regular Postgres tables, but then you can also have things that are optimized for analytics. So if you were like, I really just want one single database and I want it to do everything, Postgres probably is the best choice. And then you use extensions to make it do what you want. But then the problem with that is there's definitely a danger in mixing like the same server that's powering your app and responding to these short queries that need to respond in single-digit milliseconds. If that same server is now also being relied on for running more complicated analytics, then what happens if lots of analytics need to be run right at the same time where you have a big traffic spike, right? Like sometimes keeping those things separate is actually wiser to do, sort of for separation of concerns, right? So that way, if your website gets a big traffic spike, that doesn't negatively impact your analytics runs, and vice versa. You need to run a bunch of analytics because it's the end of the month and you need to generate reports. That's not going to negatively impact the performance of your app. So that's why one of the reasons why like some people are all into like use 50 different extensions on your Postgres instance. I'm much more in favor of use them sparingly, right? Like if you need them because it's going to help you tune performance better or compact your data better and remove data bloat, great. But I'm not a big fan of running your analytics and your OLTP workloads and your time series workloads all in like one single database. Dante says, greetings from Mexico. Hello. Doesn't Convex use this idea of transaction log ledger with OCC for linearizability? They do have something along these lines. Yeah, they're basically, I watched a good video. I won't try and butcher the explanation of it. I forget his name at the moment. Oh, I think it's Mike or Mickey. There's two Mikes that do video content and stuff at Convex, but on their YouTube channel, there's a video that I watched a couple weeks ago, which was a really good kind of overall explainer of how convex works, and it goes into some of like how things are organized at the database level. And yeah, it is kind of like a big transaction ledger, but that's powered by like MySQL and Postgres type databases. So it's pretty cool. It's a very cool technology. Yeah. Okay. Yeah. So we talked about this. There's a bunch of other stuff in this chapter. We only covered 2 of like quite a few different topics, but I think we covered some of the most important stuff. Linearizability, and then 2-phase commit and the related algorithms to this are some of the key things in here. It also talks about like distributed key value stores, things like Zookeeper and etcd, and how those use consensus algorithms for like consistent metadata storage for distributed systems. There's a number of other interesting things, but I think I talked about the main stuff that I want to cover today. So yeah, any other questions or anything? Book recommendations for what we should do next? What should we do next? We've only got 3 more chapters. So hopefully, I guess we might not do one. No, we might do one the week of Thanksgiving. Hopefully we can finish this in the next couple of weeks. And then maybe like in December, Christmas time, we can pick a new book to start going over. Maybe what we should do also is pick one that is not 500 pages. Maybe we should pace ourselves a little more for the next one. But anyway, if you have ideas, at me, message me, read some white papers. That's actually a great idea too. I like to read just regular papers sometimes. And that's actually kind of nice because it sort of time boxes things a little bit better to like, rather than committing to 12 chapters of a book, you can just read one paper at a time. And there's like lots of cool stuff you can learn. I'm trying to pull up the last one that I read. There's actually, I recently also posted about some really cool articles. There's 2 blog posts, one about one of the engineers who was early on at EBS at Amazon and another at S3. Those are really good articles. Why don't I just share my screen here? Okay. Oops, let's do this. All right. So let's see. This is a really good article on S3 by Andy Warfield, who is like one of the sort of engineering leaders of S3. They store like exabytes and exabytes of data in S3. So it's a really good read. And then this one, where was it? When was that? Yeah, this one is a really good one on EBS. But the last one that I did, paper that I read, was the Spanner paper. I'm trying to find it. Here we go. Yeah, so this is a paper I read a couple weeks ago. This is, and that's the other thing. It's cool. It's just like you can pick a paper, right? Not all companies publish papers on all of their tech. It would be cool if more did, but Google publishes their paper on Google Spanner. There's some reasons why I'm not a huge fan of Google Spanner. It's not open source. You have to run it in their cloud with their clock sync API, and it's expensive, and there's a lot of latency. But it's still super cool technology, and it's interesting to like read about what they're building and doing. Like Jeff Dean, who's like very well known in the databases and AI community, was one of the authors of this paper, right? So it's pretty awesome. So yeah, maybe we'll just do papers for a little while. I don't know. What is your recommended Postgres for beginners book? Yeah, I actually don't have a good recommendation because I don't know. I don't know what a good Postgres for beginners book is, to be honest. There was a point where I looked at some and I didn't find anything that jumped out at me as like, oh, that's the one I got to read. So you can learn a lot just by, just by using lots of Postgres. I work with, obviously, PlanetScale runs Postgres databases. You can use AI to help you learn more. I leverage AI a lot for those kind of things. Yeah, and reading papers and all that. But I guess I haven't read a lot of Postgres papers. So first time joining your session. Next time I'll prepare myself. Yeah, you don't have to prep, but if you can, read, in the next week or so, read chapter 10 of the book. But yeah, Postgres, one of the things I will say about this question is I actually do want to have a little Postgres course that I want to make. It's not an intro to Postgres course. There's other ones out there already like that. So stay tuned for more on that. It's a little different than what's out there currently. Great idea on white papers. Yeah, firecracker paper is fun. Interesting. Firecracker paper. I'm going to screenshot that firecracker paper recommendation so I don't forget. And then learn Postgres 2nd edition. Okay. I have not used it, so buy it at your own risk. But Kenway says learn Postgres 2nd edition is good. All right. Okay, well, fun. We'll finish this the next couple weeks, and then maybe we'll just read some papers. So take care, everybody. Hope you enjoyed the stream. I will see you in the next one.